has been here at Ars Electronica, which is very exciting. I had a piece here in 1996, when, of course, I was just a baby, and it was part of a larger project called the Brain Opera. So that was very exciting, and that actually brought me to my research today, which is about artificial intelligence for investigative reporting. So it was a long and complicated road to get there. Oh, do we have slides yet? Oh, they're almost there. This is very exciting. Yes, that's it. Except in English, please. Oh, there we go. Excellent. Okay, here we go. Artificial intelligence doesn't do as much as you think. One of the reasons I wrote this book is because I do a lot of presentations, and the first 10 minutes is always occupied with getting things going. So one of the things that I write about in my book and in my research is I write about data journalism, which is a relatively new field of journalism. It is the process or the practice of finding stories in numbers and using numbers to tell stories. If you're familiar with The Upshot, which is part of the New York Times, they do data journalism. If you read ProPublica, which is an American investigative journalism outlet, they do data journalism. Also, Vox and the Texas Tribune are known for data journalism in the United States. And I do a very specific kind of data journalism called algorithmic accountability reporting, where I write algorithms in order to hold decision makers accountable. So increasingly, algorithms are being used to make decisions on our behalf. And so one of the things that is the responsibility of a free press is we need to investigate those black box algorithms in order to make sure that the decisions that the algorithms are making are fair and are for the benefit of society. Now, one of the errors that usually comes up when we're thinking about artificial intelligence is the problem of Hollywood. So usually when people think about AI, they think about Arnold Schwarzenegger as the Terminator, right? He's always the first one that I think of. They think of the movie Ex Machina. Sometimes they think about bad stock art images of robots. And then also they think about Commander Data from Star Trek. Anybody think about Commander Data when they think about AI? Right? Yeah. He figures large in the imagination of a certain generation. But the thing is, this is not artificial intelligence, okay? This is totally imaginary. And this is actually how our brains work, right? Our brains get confused between what is real and what is imaginary. So when we're thinking about AI, we have to remind ourselves that we have all these Hollywood images embedded in our collective unconscious, and we need to push past that. So what's actually real about AI? AI is a branch of computer science, just like algebra is a branch of mathematics. And inside AI, as a branch of computer science, there are actually lots of different subfields. And one of the subfields is called machine learning. Now, there are other branches of artificial intelligence besides machine learning. And I see we have some AI researchers in the audience today. They're probably nodding along and saying, yes, I know about these other subfields. Expert systems are another subfield. Natural language processing and natural language generation are other subfields. But you don't hear that much about these subfields because they're not as popular as machine learning. Machine learning is far and away the most popular subfield of AI, and something interesting has happened with the language of machine learning and artificial intelligence. The two terms have become conflated. So when people say artificial intelligence nowadays, usually what they mean is machine learning. All right, so the two terms have become very confused. And this happens with language. It's very, very normal for terms to come to resemble each other, but it makes it very, very confusing for most of us who are trying to keep up with what's going on scientifically. So AI is a branch of computer science. There are other branches, but machine learning is the most popular right now. Another thing to keep in mind is the idea of general and narrow artificial intelligence. So general AI is the Hollywood kind. That's the kind that has the, that is in the popular imagination of like the computer that's going to take over the world and murder all of humankind. This idea, or the idea of machines that think. Totally imaginary. What we actually have is we have narrow artificial intelligence. Narrow AI is very real. That's what machine learning belongs to, even though it sounds, the name machine learning sounds like it's a machine that's thinking, but it's not really. Narrow AI is math. It's very, very complicated math, and it is beautiful math. One of the things that's amazing about math is it allows us to articulate the regular patterns in the universe, and that's just incredible. But it's not magic. It's just math. So narrow AI is what we have, and general AI is the fantasy. So in terms of the narrow AI that we have, I want to talk a little bit about what is machine learning exactly. And I want to talk about the Titanic, because the Titanic is a really good example that can tell us a lot about machine learning. So when you think about the Titanic, who pops into your head? You said it over here, right? Who is it? Leonardo DiCaprio, right? The Titanic, James Cameron's Titanic movie was one of the most successful movies ever made, all right? I'll bet 99% of the people in this room have seen the movie Titanic. It was one of the biggest box office hits of all time. It's part of our collective unconscious. And again, it's Hollywood that is shaping our perceptions of an historical event. When I think about the Titanic, the ship, I don't think about this black and white image. I think about how it looked in the movie. And I think about Leonardo DiCaprio and Kate Winslet and the, I am the king of the world shot, right? And also the Titanic disaster gave us a lot of data. So this is a really good learning example for doing data journalism and for doing data science in general. So what does the Titanic data look like? It looks like this. Okay, this is a very, very popular Titanic data set, and it shows who are the passengers on the Titanic. And what we can do is we can write a machine learning algorithm that will predict who survived and who perished in the Titanic disaster, which is kind of cool. We're going to do some data science right here. All right, so what do we have in our columns here? We have P class, the first one, passenger class. Are they traveling first, second, or third class? We have survived, which is a 1 or a 0, a Boolean value. 1 means yes, 0 means no. We have the name, we have the sex, we have the age, and some other information, including the fare. All right, so when we do machine learning, we have numbers. Look just like this. And what are we going to do? We're going to make a model. So this is an elementary school math equation or math activity called a function machine. And the instructions say drag each number into the function machine and look for a pattern that will allow you to complete the table. And so over on the right side of this, we have a list of ins and outs. The idea is you put a number in, and then something happens inside the machine with all the gears and things, and you get another number out. So you put in a 2, you get out -1. You put in a 3, you get out a 0. You put in a 4, you get out a 1. So what's the rule that's happening inside this function machine? -3. OK, great. So if you can handle this, you can handle machine learning. What we do in machine learning is we do very much the same process. We put in an input x, and then we've got a black box model, and then we get an output of x. And what we're going to do with the Titanic data is we're going to put in our data, And we're going to make a model. We're going to get the computer to make a model for us using some very, very complicated mathematics in multiple dimensions. And we're going to get the computer to create a model, and we're going to allow it to predict for us whether or not a person survived. Okay? So we can do this. And then the benefit of doing this is that we can reuse the model on different data. All right? So if I were an insurance company, what I could do is I could take this Titanic data, and I could use it to create a model predicting who survives a maritime disaster. And then I could use that same model to run on somebody who is applying for travel insurance for an upcoming boat trip. And I could use this model to say, all right, how much should you be charged in order to buy travel insurance? But here's a problem with this. When you look at the math of the Titanic data, it turns out that the most important determining factor on whether or not somebody survived the Titanic disaster was their passenger class. So first-class passengers survive at a much higher rate than second or third-class passengers. So if we use this in order to make our model that our insurance company is going to use, it turns out that first-class passengers are more likely to survive, and so they're going to be charged less for insurance than people who travel second or third class. And does that feel fair to anybody? No, it doesn't meet any of our social definitions of what is fair. All right? So this is one of the ways that if we depend exclusively on the mathematical or the algorithmic interpretations of the world, we're not going to match up with our social expectations. This is one of the ways that computers misunderstand the world. And there are also things that computers ultimately cannot understand. So the situation I like to think about when I think about what can't a computer fundamentally understand is I think about Jack Thayer and Milton Long, who were two passengers on the Titanic. They were young men of the same social stratum. They were about the same age. They were about the same size physically. And they both helped to save a lot of the fellow passengers. They saved babies, they saved children, and they were among the last people on the Titanic as the ship was going down. So they were standing at the rail and they watched the lifeboats pull away. And they said goodbye to each other. They said, it's time to jump. So Milton went over the railing first. He climbed over, he shook hands with his friend Jack, and he said, it's been great knowing you. And he dropped straight down next to the boat. And Jack watched his friend go over the rail. And he said, all right, it's time for me to jump. And he climbed over the rail, and Jack leaped out as far as he could away from the boat. And Jack's was the only strategy that worked. Milton was pulled down into the maelstrom, and he died. And Jack survived. He jumped far out, he swam to a lifeboat, and he survived the disaster. Now, that difference, the difference in the angle of the jump, straight down or far out, that's nowhere in the Titanic data. All right? The data looks like this. There are no angles of jumps. And there's really no way for the computer to record or even note that the angle of the jump was different. So when we rely exclusively on machine interpretations of data, we're not getting everything that we know is the complex representation of what's going on in the world. Now, it's a mistake to think that computers can do everything for us and can do everything better than human beings. Computers are really great. Literally, the first line of my book is, I love technology. And I do. Computers are a marvelous addition to our world. But what I want to argue for is I want to argue for a more nuanced understanding of what computers can and can't do. So for many years, we've been laboring under an assumption that I call technochauvinism. Technochauvinism is the idea that computers are always the highest and best solution. It's the idea that technology is better than people. And technology is not better than people. It's really about using the right tool for the task. What are you trying to do, and what is the best method for doing that? One is not better than the other. But who has told us that technology is better than people? Well, early computer scientists were mathematicians, right? Mathematics is the parent of computer science. Computer science is a descendant of mathematics. And mathematicians, for hundreds of years, have had this idea that solving mathematical problems is superior to solving social problems. They have an idea, they have a bias that math is better than people. Mathematicians are kind of snobs in a certain way. Who tells us that solving computational problems or solving engineering problems is superior to solving social problems? Or who tells us that technology is our savior when it comes to social problems? Right? We've got some folks up here. We've got Claude Shannon, we've got Alan Turing, we've got Marvin Minsky, we've got John von Neumann, we've got Larry Page, and Sergey Brin. And so what do you notice about all of these folks? They're white, they are men, all right? They are a very, very homogeneous group. They're all very intellectually homogeneous. They're homogeneous in terms of gender, in terms of their background. They're not representational of the entire diversity of human experience. One of the problems with this is that people embed their own biases in technology. Okay, so when we have a very small and homogeneous group of people giving us all of the ideas that we collectively believe right now about technology and society, that's not inclusive. That's not getting us toward more inclusive technology. And people embed their own biases in technology that they build. Sometimes it's conscious, sometimes it's unconscious. And the thing about unconscious bias is that you can't see it. Okay. There's also a factor called positive asymmetry at work. Positive asymmetry is the way that we don't like to talk about anything yucky. So when you're building technology and you're in a group of people, you tend to focus on the good. You tend to not focus on the bad. So if you are writing an algorithm to determine how much people should pay for travel insurance, you're going to say, oh, I have this great new algorithm. It's going to make things so much easier, and it's going to make things so much more fair. And you're not going to say, oh, well, this actually might discriminate against poor people and might privilege rich people. Because you don't want to say that, because it's uncomfortable. Right, so positive asymmetry is a social factor that is at work in these technological environments. And then I also want to talk a little bit about race. Have you seen this viral video of the racist soap dispenser? Yeah? Okay, a couple of people have. The way this video goes is that a man with dark skin puts his hand under the soap dispenser and it doesn't work. And then a man with light skin puts his hand under the soap dispenser and it works. And the light-skinned man puts it back under. Then the dark-skinned man takes a white paper towel and puts it under the soap dispenser and it works. Right? It's absolutely horrifying. So we've known for years that image recognition systems, which is what's embedded, which built into the soap dispenser, image recognition systems do not recognize people with darker skin. We've known this for years. Nobody has done anything about it, in part because it's a very homogeneous group of people who are making the technology. And there has not been a lot of will on the part of technology makers to fix this feature. Okay? However, what scares me is the way that these kinds of naive algorithms are embedded in technologies like self-driving cars. So self-driving cars also rely on image recognition algorithms. They're the same kinds of image recognition algorithms that are in the soap dispenser, which doesn't work very well. And so these image recognition algorithms that are in self-driving cars are actually so naive that you can defeat them easily. So if you put a sparkly unicorn sticker onto a stop sign, the self-driving car would no longer recognize this as a stop sign, and it would just blow right through, and it would cause an accident. Now, that doesn't seem safe to me. And I don't know about you, but stop signs are, I see a lot of graffiti on stop signs. I see signs regularly defaced out there in the world. So that's going to lead to more situations like the situation we recently had in Tempe, Arizona, where a self-driving Uber killed an innocent pedestrian. So this is one of the reasons that I think we need to push back against technochauvinism. We need to push back against the cognitive biases that Nathan mentioned that are very, very common in our human experience. They're not bad, but they do necessarily bad, but they do exist. They're a part of the errors that are a part of our lives, and we can embrace them. All right, we can make technology that is inclusive. We can make technology that does account for human error, and that's going to get us to a much better world. Thank you very much.